Oops. All right. Good morning, lads and ladies. Welcome back. Today, we are entering into our last sort of little chunk of the class where we're going to talk exclusively about systems of equations and inequalities. There are a bunch of different kinds of systems, and I don't think you will find this especially challenging, but there are a few new techniques that I want to make sure everybody actually internalizes and actually learns. So we're going to start off keeping it gentle, talking about the sort of systems that we looked at as a little preview last time, and then we'll slowly ratchet it up to talking about nonlinear systems and more complicated methods for solving. Oh, what just happened there? Something. So I need just one moment. All right. That worked. I think so. Weird. Okay, let's try one more time. Why would that have gone to here? That should have worked. All right. Yes. Okay. All right, let me turn on the screen share. We can get started. Pop the quiz as well. So systems of linear equations, I think, can be difficult to motivate and show how exciting they are at this level. So I want to do my best to kind of preview for you the perspectives from which we'll be thinking about these things as you move forward. In pre-calculus, we learn how to regard systems of equations as matrices, and that's sort of the first level of abstraction. I definitely won't be doing that to you here, but I do want to kind of motivate the way of thinking. So let's do that, and let's also look at some applications. This is MAC 1105, section 015, which is college algebra. And the date today is the 12th of April, 2022. We'll be talking about systems of equations. Something else I want to do, I want to talk to you guys a little bit about our last midterm. So we haven't set a firm date for this yet. And exactly what we do kind of depends on how much time we want to leave available for the final exam and preparing for the final. In this class, I think it is wise to leave at least a day for the final, maybe two if we can. And because we are nicely on schedule, I think that is the case. So let's take a quick look at the calendar here. The 22nd is the last day of class. So for us, the 21st is our last regular class meeting. Homework 20, which is on systems of equations, that's going to be due on the 14th. That's the material we are covering. And then systems of inequalities would be next Tuesday. Oh, actually, I guess we don't have an extra day. For some reason, I thought we had an extra day in here, but we do not. All right, so let me just make the announcement then. We don't need to have a discussion about it. Exam 3 will be on 4/21, which is our last regular day of class. And then the final exam was also, do a little reminder for that. So the final for this class is a department final. It is not a test that I write. It is the same test for all college algebra classes. And your final is going to be on the 26th at 10:30. So that is the Tuesday after next, 2 weeks from today. Tuesday, 4/26, 10:30. So I just want you to be aware of these things. If you have not already, please put the date of the final in your phone's calendar. Make sure you set up a few notifications to remind yourself it's not our normal class meeting time. And it's possible that you could run into some trouble if you don't take special care. There's a question that came in the form of a DM here. So yes, the final exam will replace your lowest midterm exam if the score on the final is better. So if your lowest midterm is like a 50 and you get like a 70 on the final, then the final will count as that 70 for the final. And in addition to that, I'll go back and replace your lowest midterm, the 50, by a 70 as well. Alrighty. So yeah, let's get to it. A system of equations is a collection of equations meant to be solved simultaneously. Generally, you'll have some number of equations, each having the same variables, multiple variables. Most of the time, you'll have the same number of variables as you have equations. And the idea is to find values for all of the variables that satisfy all of the equations at the same time. We looked at one example the other day. Before I get into examples, I want to classify these. Into two groups. Linear systems. Now I'm going to explain what these are here, so leave a little space in your notes. And nonlinear systems. I heard a mathematician once joke that classifying systems as linear and nonlinear is like classifying all the objects in the world as bananas and non-bananas. Like it's kind of a ridiculous thing to do because, you know, most things are not bananas. Most systems are not linear. But at the same time, it's a valuable classification scheme because linear systems, we know everything about. And what I mean by that is that the field of mathematics that's built around the theory of linear systems called finite dimensional linear algebra is completely understood. There really aren't any new theorems. It's done, right? Which is a weird thing to say. Mathematics is never done, with the exception of this field here, right? There's always new theorems and new things to discover, but we pretty much know everything there is to know about linear systems. This is where all the equations are linear in all the variables. And we talked earlier in the semester about how to classify an equation as linear or nonlinear, right? How to classify a function as linear or nonlinear. If any of the variables are raised to a power other than 1, if any of the variables show up downstairs in a fraction, anything like that, then that equation is nonlinear. So if you have a system of equations where there's a single instance of x squared or a single instance of 1 over y anywhere in any of the equations, that automatically ruins this, right? You need every single equation to be linear in every single variable. A nonlinear system, you can probably guess, is one that's not linear. So this is one where any variable in any equation downstairs in fraction or raised to any power besides 1. All right, if any one of the equations is nonlinear in any one of the variables, then the whole system is called nonlinear. So just an example of the classification scheme. This is a linear system. Both of the equations here are linear equations because the variable x in the first equation and the variable y in the first equation only show up upstairs and only show up to the power of 1. And the same is true of the second equation. The system here is nonlinear. Right, because of the x squared. What about this guy? Is this third system down here linear or nonlinear?
Non-linear?
So I definitely put a bunch of stuff in here that's trying to make us think about it, right? Like e to the pi and the square root of 2 and 1/2. Those seem like potentially nonlinear things, but remember what we're looking for. We're looking at the variables. So here, this x, he's upstairs and he has an x to the 1. Here, this y is being multiplied by the square root of 2, but the y isn't under the square root. This is just a y to the 1. And down here, we've got some fractions, right? Like a 1/2. But again, the x is just being raised to the first power. And 6y, that's certainly linear. This is actually a linear system. If you write down random combinations of equations, yeah, odds are it's going to be nonlinear because the majority of equations that you write down, if you just start writing down random shit, will include powers of variables and exponentials and all sorts of things that are not themselves linear. But linear systems are nice to think about as a separate thing because, like I said, we know everything about them. In particular, we have two methods that will always work to solve a linear system if that system has a solution. Nonlinear systems, on the other hand, there's really only one method that we can learn at this level that will work for nonlinear systems, and it doesn't always work. There are many, many nonlinear systems that we just can't solve by hand. There's so many of them. And in that case, what we need is computers to do their best to approximate solutions using what are called numerical methods. And numerical methods for solving nonlinear systems of equations, another whole big field of mathematics. If you, for whatever reason, feel compelled to torture yourself and go to graduate school for math, odds are at some point you will be forced to take a class on numerical methods, which is computer programming aimed at solving things like nonlinear systems of equations. Great. Let's talk about how to solve linear systems. Or maybe it's better, let's start with a nonlinear system. We can get that out of the way because we're not going to spend much time on those. We're definitely going to be focused on linear systems. But we'll knock out the nonlinear system stuff first. So we mentioned last Thursday, but it bears repeating. We can attempt to solve any system, linear or not, by graphing the equations. The solution or solutions, there might be more than one, are the points where the graphs touch. This is not a good method. In fact, it's not even a method really, but it's a reasonable way to get a feel for what's going on with the system. You can look at the graphs and say, ooh, these graphs do touch. So there is a solution. Let me go try to find it. Ooh, these graphs don't touch. There is no solution. Let me throw this one away. So let's sketch the system. And we'll do something like, I don't know, how about y minus x equals 0 and y squared plus x squared equals 1. And approximate any solutions. Oh, actually, you know, I'm going to modify this just a little bit because I'm realizing that our graphing calculators can't quite handle the second guy. Yeah, get rid of the square on the y. We're just going to look at y plus x squared equals 1. So I'm going to pop up Wabbit and get our calculators out. Waiting for that, I'm going to go ahead and draw myself a little coordinate thing. We could sketch this by hand. What I'm going to do is solve each equation for y. That way I can plug that into my calculator. And we'll call this first guy equation 1. And we'll call the second guy equation 2. Equation 1 says x equals 0. And saying y equals x. Equation 2 says y plus x squared equals 0. Oh, sorry, equals 1. Which means y is 1 minus x squared. These two equations solve for y, which will allow me to plug them into my calculator. That's y equals x for the first guy, and 1 minus x squared for the second guy. And we can take a look at that graph. There's y equals x, and there's 1 minus x squared. It does look like these two graphs touch each other. We can try fiddling around with the trace function, but we're zoomed out so far that I can't really see what's going on. So let me play with my window settings. Let's change this -2 to 2. And we'll do that for the y-axis as well, and see if that gets us to a place where we can see a little better what's going on. Oh, there we go. So I see what look like two solutions. I see one here, and I see one over here. I can fiddle with my trace function to sort of try and approximate this. This one solution looks like it's about 0.59, 0.59. And the other fella over here looks like it's about negative 1.57. So let me sketch these. And these sketches, they don't need to be works of art. But we can see that this quadratic here, this is a parabola opening down. He's got roots at -1 and 1. Y-intercept is the vertex at 0, 1. So I'll tag this as 0, 1, 0, 0. Here's the graph. Like that. And then the other fellow is the line y equals x. Let's say line to the origin, slope 1. Looking something like that. So my two solutions are these two intersection points. And from the graphing calculator, I can see that they are approximately 1.57, 1.7, and this guy's somewhere around, let's see, 4.6 or something. Yeah, let's call it 0.6. Now those are approximate. And if I want to describe the solutions nicely, I would say there appear to be two of them. Each solution is going to be an ordered pair, right? An X and a Y. So that means there's 4 numbers involved altogether here. The one solution is X equals 0.6 and Y equals 0.6. The other solution is this guy, X equals -1.57, Y equals 7. Again, just approximate solutions. So the question arises, if I want to find the exact solutions, can we do that? The method we talked about last Thursday, just very briefly at the end of class, will allow us to find the solutions here. So we're going to talk about substitution. For nonlinear systems, this is the only way to go. For linear systems, you can do this, but there is a better way called elimination. I'm going to teach you that as well. The procedure for substitution, and this, I should say, this works for linear and nonlinear. First step is to solve one of the equations for one of the variables. The second step is to plug the result from step 1 into the equation you didn't solve, right, into the other equation. That's going to give you now an equation with only one variable. So you're going to solve the resulting equation from step 2. And then finally, you're going to do what's called back substituting. A solution from 3 into either original equation. and solve for the other variable. It sounds harder in words than it actually is in practice, but I think it's wise to have these steps written down somewhere, so if you ever get lost, you can refer back to them. So the first step, pick either equation, doesn't matter, solve it for one of the variables. I usually choose whichever one is easier to solve for one of the variables. Now you have, like, say, y equals something. You're going to take that and plug it into the other equation for y. That'll give you an equation that only has x's in it. Since that equation now only has x's in it, you can actually solve that equation. You can solve that equation and get a number out, like x equals 3. Once you get that, say x equals 3, you take it and back substitute or plug that into either of the original equations and solve for y. And it does not matter which one of the original equations you back substitute into. So again, this is called substitution, and it's usually the first method people learn for solving any kind of system. Let's see if we can solve the system that we just approximated the solution to. Y minus x equals 0, and y plus x squared equals 1. Solve this using substitution. Oh, we actually already solved one of the equations for one of the variables, right? We solved that first equation for y. We solved both of the equations for y. So I'm going to step 1 here. I'm going to solve y minus x equals 0 for y. So y equals x. Step 2. Substitute y equals x into the other equation. Plug into y plus x squared equals 1. Okay, well, this just means everywhere you see a y, you should write x instead. So that means x plus x squared equals 1. Now I have an equation with only one variable. I can try to solve that for that one variable. Okay. How do I solve this equation? What should I do here?
Add the x's, divide by 2.
I cannot combine these x's. So one is a regular x, the other one is an x squared.
Set it equal to 0 and then solve by factoring.
Yeah, that's a good attack. So it's this is a quadratic, right? I've got an x squared and an x. So I should first pull everything to one side. That's necessary no matter what. I'm going to write the x squared out front. So I've got x squared plus x and subtract the 1 over, minus 1 equals 0. And yeah, the standard approach, first thing we should try to do here is factor. Can I factor this? Are there two numbers that multiply to -1 and add up to +1? Or can we find two numbers that multiply to -1 and add up to +1? Well, there's only two integers that multiply to -1, and that's 1 and -1. And no matter how you add those, they're going to add up to 0. So this doesn't look like it factors. At least not by hand. So we can use the quadratic formula. Remember that says x is negative b plus or minus the square root of b squared minus 4ac all over 2a. Where a, b, and c are the coefficients of x squared, x, and the constant. So negative b is -1 plus or minus the square root of b squared is 1 squared, which is 1 minus 4 copies of a times c, that's 1 times -1, all over 2 times 1. So let's clean this up. I get -1 plus or minus the square root of, let's see, 1 minus, and then 4 times 1 times -1. So that's 1 minus -4 is 5 all over 2. So I get two solutions. X is either -1 plus the square root of 5 over 2, or x is -1 minus the square root of 5 over 2. So these would be the answers from this step. And then our last step is to back substitute these into either original equation. And for my money, it's much nicer to back sub into the first equation. I'm going to back sub into y minus x equals 0. So on the one hand, if x is -1 plus the square root of 5 over 2, then y minus -1 plus root 5 over 2 equals 0 means that y, just add the whole thing over as a chunk. This is y minus some number. So I'm just going to add that all over. Y is -1 plus root 5 over 2 as well. Therefore, one solution. I won't even write it like this. I'll just say, boom, boom. This is your first solution. X equals that, y equals that. On the other hand, if x is -1 minus the square root of 5 over 2, then y minus that, -1 minus root 5 over 2 equals 0, which means y is -1 minus root 5 over 2 as well. So here's my second solution. And we can see how far off we were with our approximations. As decimals, these two solutions are here. I'm going to put the whole top in parentheses because that's what we do with fractions that have more than one piece upstairs and downstairs. -1 plus the square root of 5. Get out of the square root, close the parentheses, divide by 2. So that's 0.6180, blah, blah, blah. And the x and the y here are the same. We have 0.618 and y equals 0.618. And the other one That's parentheses -1 minus the square root of 5, close parentheses, divide by 2. And that's -1.618. And the y there was the same thing, -1.618. So these are the two solutions to that nonlinear system. And it was a bit of work, right? Questions about any of these steps? Can't quite fit it all in here. I'll hold this for a minute. Okay. That's about the whole story for nonlinear systems. All we can do is substitute. That's it. And the procedure goes pretty much the same every time. When you get to this step here, step 3, this will vary depending on the types of equations you have. Right? There are many different kinds of nonlinear equations. Sure, here we ended up with a quadratic, but we could have ended up with a logarithmic equation, an exponential equation, an equation involving rational functions, all sorts of things. So it's not the case that you're always going to use the quadratic formula. It's not the case that you're always going to get 2 solutions to the resulting equation here. Sometimes you'll have 1 solution, sometimes you'll have none, you could have many. But the general procedure is always the same. You solve one of the equations for one of the variables. You plug or substitute that result into the other equation. That will give you an equation with a single variable, which you then solve. You take whatever solutions you get there and you back substitute them into either equation to find the corresponding value of the other variables. So when x is this, we found y is this. When x is this, we found y is this. So the 2 solutions are x and y here, that's 1. And x and y here, that's 2. Okay, last call for questions on this one. I'm not going to talk anymore about nonlinear systems because honestly, they're not that interesting. I mean, they're I should say the theory is not that well developed. That's the better way to say it. On the very bottom, yeah. So use the solutions as decimals. All right. So our approximation wasn't off by much. We were pretty darn close. And that, you know, the graphical thing is a valuable thing, but it won't get you exact solutions. Let's see if we can use the same method to solve a linear system. 2x minus 4y equals 3, and x plus y equals 1. And we'll solve this by substitution as well, just for a little more practice. We could graph these. That's an option. We could solve both of these for y and graph them, but you don't need to do that in order to solve the system. Our first step is to pick one of the equations and solve for one of the variables. I think the second equation is easier to solve for one of the variables, so let me go ahead and do that. This means y is 1 minus x. Then we're going to substitute that into the other equation. So everywhere there's a y in the first equation, I'm going to write 1 minus x instead. This will become 2x minus 4 times 1 minus x equals 3. And then we're going to solve this. And because this is a linear system, the equation solving here, we're just working with linear equations. There's nothing fancy. We need to distribute that 4. And so I want to point out that these parentheses are important, right? If we plugged 1 minus x in here, and we didn't put these parentheses, then we would end up with the wrong answer. That 4 is supposed to multiply all of y, and y is 1 minus x. So that 4 needs to multiply all of 1 minus x. So I'll go ahead and distribute the 4. That'll give me 2x minus 4 plus 4x equals 3. I have some like terms on the left-hand side. I've got 2x and 4x. Those add up to 6x. Sorry, 6x minus 4 equals 3. I can add the 4 to both sides, and that'll give me 6x equals 7. And then I can divide both sides by 6, and that'll give me x equals 7/6. Now I can back substitute. I have x equals 7/6. I can plug this back into either of these equations. Does not matter which one. I think it's easier to plug it into the first, or sorry, into the second equation. So let's do that. X plus y equals 1 is going to become 7/6 plus y equals 1. And then if I subtract 7/6 from both sides, I get y equals 1 minus 7/6. I can do this subtraction by having a common denominator. 1 is the same as 6/6. So 6/6 minus 7/6 is negative 1/6. So y is negative 1/6. And you see this process is a little bit simpler with linear systems because there's never any quadratic formula. You're only going to get a single solution from the substitution step. So our solution is the single ordered pair x equals 7/6, y equals negative 1/6. And you could write that as a point. 7/6 comma negative 1/6 if you want. Sometimes you'll see people writing solutions to systems as ordered pairs rather than as separate x's and y's. It's the same thing. Just for shits and giggles, I'm going to graph this system for us in Desmos, and then we're going to talk a little bit about the possible solution cases. Before I do that, are there any questions on the procedure here? I realize I kind of combined step 2 and 3 here because it's just so simple. Yeah, so I should say, sorry, this is 2 and 3, and this is step 4, and the numbering system we had. All right, let's take a peek at Desmos. Always a fun. I had 2x minus 4y equals 3, and x plus y, y equals 1. And we see these two lines, and we see that they touch right here. And if I enter in the ordered pair, 7/6, comma, -1/6, boom, that's our guy. So this system had one solution. I'd like to think now a fun question. I'll say solution cases for a linear system of equations with two equations and two variables. So it is possible to have a system with many equations and many variables. We are focused in this class on what are called 2x2 systems, systems with two equations and two variables. In other words, we're asking, how can this picture change? This is the same as asking, how can two lines intersect? So if you have two linear equations, each equation, the graph of each equation is a straight line in the plane. And we know that the solution is the point where those lines touch. So the question is, we take do I not get a slider for, oh, I've already got a slider for B, A plus C. So the question is, if I allowed all possible lines, we can move these around. What can happen here? Will they always intersect? Or is it possible for them to not intersect? Could they ever intersect in more than one point?
It won't intersect if they're parallel.
Very good. Yeah, if the two lines are parallel, then they will never intersect. Right? If the two lines are not parallel, then what can we say?
There's going to be a solution for them, the lines to intersect.
Yeah, they'll intersect, and they'll intersect in one point only, right? If I have two lines that are not parallel, then they'll intersect at a single point, which means there's one solution, one ordered pair, one point that lives on both lines. There's a third possibility. Can anybody detect a third possibility?
I forgot what it's called, but it would be all solutions if they're on top of each other. Both lines are on top of each other.
That's the idea. I would be a little bit careful with the language. So the possibilities are, if the lines are parallel, but distinct, meaning same slope, but different y-intercept, then there will be no solution. Because these lines never touch. This is actually an axiom from ancient Greek mathematics called the parallel postulate, that two parallel lines never touch. So if the lines are parallel but distinct, in other words, same slope, different y-intercept, then there's no solution. That's one possibility. If the lines are not parallel, right, different slope, I don't care what the y-intercept is, then there will be one solution. We call this a unique solution. Right, unique in mathematics means nothing else in the world like it. Only one. Not like people like to use the word unique with qualifiers like kind of unique or more unique. But in mathematics, unique means one and only one. And then that third possibility is kind of interesting. The lines are identical, meaning same slope and same y-intercept. Now, in this case, I don't want to say all solutions because it's not true that every ordered pair is a solution, right? Like here, -10, 0 is not a solution. That is an ordered pair that is not on this line. Right? Or sorry, -10, 0 over here, not 0, -10. Either way, this guy, not a solution. But there are infinitely many solutions. Every point on this line is also on this line. So every point on that line is a solution. And the careful way to describe that, we would say that there are infinitely many solutions. And we need to talk about how to describe those solutions, because the trap that's easy to fall into is to say something like all real numbers, even though we're talking about ordered pairs, but we need to be more careful. We need to find a way to characterize, to describe exactly what points are solutions and what points are not solutions in this third case where there are infinitely many of them. So that requires a little bit of love, and we're going to do that. Before I show you how to do that, I want to show you another method for solving. I want to show you the superior method for linear systems. So regardless of which case you're in, the best method for solving linear systems is called the 1 L or 2 L. I don't know, I can't spell it. It's 1 L. Elimination. Now that looks wrong to me too. You ever have one of those days? Elimination. Elimination. Oh, 1 L. Okay, that's right. So, what is this method called elimination, and how do we use it? Before I move away from this page, any questions on what we're discussing here? Okay. What is it about systems that make them hard to solve? Why is it not the case that I can just like, why do I need a method at all? Why can't I just come in here and be like, all right, I'm gonna solve the first equation, I'm gonna solve the second equation, and now I've got my answer. Why do I need any of this bullshit?
Because we put the two together to find the solution of the two, rather than just the solution of one.
There's that. Yeah, that's a thing, right? I need to make sure that I'm solving both equations simultaneously. And so if I was somehow to solve this one and then solve this one, there's no reason for those two things to be connected to each other necessarily, right? You know, if you solve some equation on Tuesday and some other equation on Wednesday, you don't necessarily expect the solutions of those to have anything to fucking do with each other. That's a good answer. Mechanically, though, can I solve this and get like y equals 5 or x equals 1 plus the square root of 5 over 2? What is it about this first equation or this second equation, either one, that prevents me from solving one of them on their own and getting a number? Not a trick question. There's two variables, right? Each of those equations has two variables, x and y. Like I can solve the first equation, but I don't get y equals 5, I get y equals x. So if I'm trying to get a number out from solving an equation, that equation needs to have a single variable in it. Cannot have more than one variable. If an equation has more than one variable, the best we can do is solve for one variable in terms of the other, right? So instead of getting like y equals 3, I get y equals x. The point of the substitution method, the real money comes here, right? Where you plug the y equals x into y equals 1 minus x squared to get your quadratic, because that gives you an equation with a single variable. Elimination is called elimination because it allows us to eliminate one of the variables. And that will yield an equation with one variable, which we can then solve. So this is the method that led to the discovery of linear algebra, which, by the way, I know I said it's kind of completely done. There's nothing more to do there. It's all solved. Is still a very beautiful thing, 100% worthy of your time. Myself, I've taken 3 classes in linear algebra, and each one of them was like really enlightening and beautiful. It turns out this is the field of mathematics where the whole concept of a dimension is defined for the first time and clearly. So if you're interested in higher dimensional spaces, trying to understand 4D space, 5D space, or even infinite dimensional space, then linear algebra is for you. And this is sort of the gentle introduction to linear algebra learning elimination. The steps are like this. What you want to do is look at your 2 equations and multiply through one of the equations by a number such that the coefficients of one of the variables becomes the negative of the coefficient of that same variable in the other equation. It sounds scary, but step 1, multiply one of the equations by a non-zero constant chosen to make the coefficient of one of the variables the negative of the coefficient of that same variable in the other equation. So if the coefficient of x in the second equation is 2, then you would multiply through the first equation by some constant to make the coefficient of x in the first equation -2. So the first equation would have like a -2x and then some other shit. And the second equation has a +2x and some other shit. We do this so that we can then add the two equations. Which eliminates the variable that you're fucking with in step 1. Then, so you add these two equations, the x's go away, or maybe the y's go away, depends on you, it's your choice. That's going to give you an equation with one variable, which you can solve. And then you back sub. Back substitute the result from 3. And just like in elimination, you can do that into either original equation. So definitely step 1 is the money step here. That's the step that kind of sets us up. That's where all the thinking takes place. Everything is very mechanical after that. I'm going to show you how to do this, and then I'm going to show you what each of those 3 solution cases look like when you proceed this way. I'll hold here just for a minute. Anybody still writing? Here we go. Let's see. Yeah. That is out of focus. We're going to solve this system. Focus, fuck. 3x minus 2y equals 1, and 6x plus y equals 0 using elimination. It is entirely possible, by the way, that you encounter problems, say on the final exam or elsewhere, that require you to solve by elimination. So it is the case that we must learn this method. So what I want to do is pick a variable to eliminate. We can eliminate the x's or we can eliminate the y's. certainly both are possible here. I'm going to eliminate the x's. In order to do that, I want to multiply through this first equation by some number that makes the coefficient of x here the negative of the coefficient of x here. So the coefficient of x in the second equation is 6. That means I need to make this 3 into a negative 6. So I'm going to multiply through the first equation, which I'll call equation 1, by negative 2. And you have to do it everywhere on both sides of the equation. So that's going to give me negative 6x plus 4y equals 2. Oh, sorry, equals negative 2. The second equation I leave alone. 6x plus y equals 0. Now we're going to add the equations. I like to think of it as like a vertical addition, so we're just add the columns. So negative 6x plus 6x is 0x. 4y plus y is 5y. And negative 2 plus 0 is negative 2. The x's are gone. This just says 5y equals negative 2. Now we're going to solve that equation. Divide both sides by 5, you get y equals negative 2/5. Back substitute. Again, we could back sub into either equation, it doesn't matter. I'll go ahead and back sub into the second equation. I'll use equation 2. So we have 6x plus negative 2/5 equals 0. That's the same as saying 6x minus 2/5 equals 0. That's the same as saying 6x equals 2/5. And now we encounter one of those funny fraction things we talked about last week. This would mean x is 2/5 divided by 6. Now, who wants to remind me how we handle this apparatus? I don't like that answer. That's an ugly answer.
Parentheses
Where do they go?
around the 2/5.
Very good, right? I'm taking the rational number, the fraction 2/5, and I'm trying to divide that whole thing by 6. So this is 2/5 divided by 6, which I should think of as 2/5 divided by 6/1, right? 6 is 6/1. Now we flip and multiply by the bottom to get 2/5 times 1/6, which is 2/30, or 1/15. So our solution here is x equals 1/15 and y equals negative 2/5, which again we could write as an ordered pair. 1/15, comma, -2/5. Cool, right? Now this is about the same amount of work as substitution. And this wasn't really faster. The advantages of this method, though, right? The systems we've looked at so far, the linear systems we've looked at so far, all had a unique solution. There's one point where those two lines touched, one ordered pair that solves the system. The substitution method is not very good at detecting the other cases. No solution and infinitely many solutions cases. What's worse is that as you add more and more variables, so if I had a system of 3 equations and 3 variables, the substitution method takes way longer, like way longer, but the elimination method stays the same amount of work. So the elimination method is superior for 2 major reasons. The elimination method is much better at detecting those weird solution cases. And also it generalizes to higher order systems much more cleanly. Now, this is college algebra. We're not going to dig into 4x4 and 5x5 systems. I'm not going to do that to you. We are going to require you to get comfortable with the other 2 solution cases, though, the no solution and infinitely many solution cases. So I want to show you how the elimination method looks on those. Where are we here? It's 10:43, so we're a little short on time. I may, we can go ahead and do one. Let's take a look at this guy. I want to solve this by elimination. So I'm going to multiply equation 1 by some number that will get rid of the x's. Looks like if I multiply by 2, that will give me 4x plus 2y equals 2. And the other equation I leave alone, negative 4x minus 2y equals negative 2. And I add the equations. I get 4x plus negative 4x, that's 0x. 2y plus negative 2y, that's 0y. And 2 plus negative 2, that's 0 as well. This just says that 0 equals 0. And that's how you know there's infinitely many solutions. This is called a tautology. How do we describe those infinitely many solutions, though? Well, remember, if there's infinitely many solutions, that means that these 2 lines are really the same line. So every point, these are the same lines, which means that every point on the line is a solution. So how do you describe all the points on the line? Well, let's take that first equation and solve it for y. We get y equals 1 minus 2x. So a generic point on that line every point of the form x comma y equals x comma, if we're on this line, then y is 1 minus 2x is a solution. And I want to be clear, that's not the same as saying all points in the plane solve the system. The point 0, comma 0 does not solve this system. But if you plug in 0 for x, you can find a point which does. 0, comma 1 minus 2 times 0 is a solution. So when x is 0, we get 0, comma 1. When x equals -1, we get -1, comma 1 minus 2 times -1 is 3. Is a solution. When x equals +1, we get 1, comma 1 minus 2 is -1 is a solution. And I could keep going like this. Plug in any number for x, and you will get a solution. So this is how you characterize or describe all those solutions at once. And if you want to start listing specific solutions, you just plug in a number for x. Any number you plug in for x will give you a solution. I know that we are over time now, but I don't want to let you go without showing you one system which has no solution, just so you can see what that looks like. This, though, I think is generally the toughest part of this section. So are there any questions about how we came up with this description of the solutions, or how we're getting specific ordered pairs out if we want them? Oh. Very quickly. This looks quite similar when we run through the procedure. Again, I'll choose to eliminate x. So to eliminate x, I'm going to multiply equation 1 by the number 2. That will give me 2x minus 2y equals 6. And the second equation I leave alone. This time, when I add the equations, all the x's and y's will go away. But the right-hand side is not going to be 0. So negative 2x and positive 2x, that's 0x. Negative 2y and positive 2y, that's 0y. 6 plus 1, though, that's 7. Now 0x plus 0y is still 0, so this says 0 equals 7. This is called a contradiction. 0 is not equal to 7, and that tells you that there are no solutions. And that's it. So if you get a contradiction, there are no solutions to that system, right? You eliminate one variable, the other variable gets killed too. If you get something like 0 equals 0, you've got infinitely many solutions, and you need to go on to characterize them as we did in the previous example. If you get something like 0 equals 7 or 0 equals -5, that's a contradiction. That is not a true statement. That's never true. And that means there are no solutions. The majority of the time, though, you're going to have a unique solution. So those first few examples we did, those will be most represented in your homework. that's all I have for you guys today. On Thursday, we're going to talk a little bit about systems of inequalities. We're going to do one more activity, and then we'll start getting ready for the test. So if you have any questions, anything you want to talk about, you can come see me in office hours, send me an email or a Canvas message. You all know the drill at this point. We're getting close to the end of the semester. So if there's any homework that you haven't done or you need to catch up on, let's get on that ASAP. Don't drift into the end of the term with stuff unfinished. That is it for me. I'll see you guys on Thursday.